All right, people, here we go. Sampling distributions. This is for sample proportions. Sampling distribution, sample proportions. That's 7.2. So I'll add that in here. Sample proportions. All right. So thinking about the activities that we did in class, right? We spun pennies around, right? Flipped them, learned how to do that. They landed, probably ended up kind of 50-50, just like a coin flip would be, right? So we had this from class. So I would copy this from your class. I'm going to put some stuff in here that should be kind of similar to what we saw in class, but since that class hasn't happened yet, it's kind of just like generic, okay? But you can put your actual ones in here because that means a little bit more because you did it. All right, so the population distribution, if it's around 50-50, which spinning pennies should be pretty close to, we probably got a population distribution that looks something pretty close to 50-50, right? So if this is 0.05, sorry, point 0.5, my bad, 0.5. So 50% chance of happening, 0 to 1, 0.5. It's 50-50, right? Heads, tails, right? When our sampling distribution went up, when we sampled four, when we flipped four coins, right? Or spun four coins at a time and saw how many heads landed and found that proportion, we noticed something change, right? When we went from 0 to 1 with a zero point 0.5 in between, we got something that kind of built up probably something like this, right? Where it was more in the middle and less on the sides. And it kind of made sense to us, right? Just kind of mounding up. When we went to something bigger, and I don't remember what we did. I'm going to put 16 here. Again, put what we did in the class here is fine. We probably noticed that as we went along, we got a lot of stuff in the middle, and the ends kind of squished in as well, right? It was very unlikely to get zero heads out of 16. It was very unlikely to get 16 heads out of 16. We probably got something that looked a lot more like this, right? And again, I'm just kind of throwing out there what we probably got. And we might have gotten something over here, it might have looked like that, but we're getting something that looked like that. So we can see what happens as our sample size increases, right? With something that was 50-50 to start with, right? All right. So thinking about that, and let's move to our next one. We did the Skittles, right? You had 20% of your little bag or cup was filled with your favorite flavor of Skittle, and we randomly pulled them out. So the population distribution probably looks something like this, right? We got 80% of the time, something around there, we would get zero Skittles. And 20%, if we do just one at a time, we would get one Skittle, right? So our population distribution look like this. This would be no Skittles. This would be, we got one Skittles out of one, right? Kind of population distribution you could think of as a sample of size one, right? When our sample size went up, though, something changed, right? And again, this may be different from your class. If this is 0 and 1, 0 0.5, I'll do the same thing here, 0 0.5. Let's use the same scale from 0 to 1.0. We probably ended up something that looked, I don't know, I'm going to guess probably something like this, right? One of these are kind of about the same, and then it kind of went down and then went down and then went down, probably something like that, right? So we're spreading out a little bit, but it's kind of looks a little different than this, right? We can kind of see some changes. And then we went to something bigger. I'm going to put 16 here. Again, it may have been something different. Again, put what we did in our experiment down here. Because that'll mean something more because you did it, right? When we went to 16, it was pretty unlikely to get zero, right? But it still happened every once in a while, probably. But we probably built up a distribution that looks something more like this, right? Um, I don't know. I'm kind of guessing. It probably should have been a little bit more this way, right? And then going down. That was bad, Mr. Reba. Something like that, right? That's my guess. All right. So pretend those didn't happen. We notice all of these. Yeah. There we go. We probably notice that all of these, the average or the mean of our samples was right around a half, right? Or pretty close to it, is my guess. All of these, we noticed our mean was right around zero point 0.2, right? The mean here was about zero point 0.2. The mean here was about zero point 0.2, right? It stayed consistent. So some things that we learned. For both examples, what happens? What happens to shape? As sample size went up, what happened to our shape? Here it was uniform and it turned more into kind of a normalish curve, right? Here it was definitely skewed in one direction, right? And then as we went on, it became more closer to normal. So as sample size increased, it became more normal, right? Obviously, this one became more normal faster than this one did. This one, even on the sample size of 4, kind of looked kind of normalish, right? This one definitely still looks skewed, right, at a sample size of 4. But by the time we got to 16, we were getting pretty close. We're getting pretty close. All right. What happened to the center? Stayed the same, right? Stayed around the population parameter, okay, which is pi or p, right? The true population proportion, right? This one stayed about 50%. This one probably stayed right around 0.2%, right? And then the spread, what happened to the spread? We went from 0 to 1, like full spreads on these ones, right? And then it's kind of squishing in, right? Squishing in. So as sample size increased, we got less variability. Oops, sorry. Less variability, right? We squish things in. Um, so let's do this. The cool thing about sampling distributions that I said before is they're going to lead to something else. You never do this in real life. You never take 8 million samples from a population, right? What we know, or why we're doing this, is that we know that as sample size increases, some predictable things happen. And we're going to use that predictability to help us answer questions in the future. Okie dokie. So if we grab our green sheets, okay, turn to that first page. It goes down at the end of it. It says sampling distributions, but there's nothing here that's really fun for us yet. Confidence intervals are coming soon, um, but we'll turn the page. And at the very top of the page, we see sampling distributions, continued, sampling distributions for proportions. That's what we're working on. It even says that on the formula sheet. So if I'm ever looking, if there's a question about sampling distributions, I could turn here, and this might be stuff that helps out. Okay, so we're going to write some things on here. So for one population, p hat is our sample proportion. I'll allow you to write that down. We'll eventually be so good at knowing that p hat means sample proportion, we'll never need to look at this, right? Proportion, but for now, that can be helpful. This is the mean of the sample proportions, right? So mean of sample proportions, right? Oh, we'll write that. Why not? Mean of sample proportions equals this, which is equal to pi. This is the population proportion. Okay, it's our parameter, right? This is the standard deviation of sample proportions. Standard deviation of sample proportions. And we've got the formula here. We've got the population proportion times 1 minus the population proportion divided by n. I don't think we need to put anything there. We've already defined it there. Okay. Notice here we have the standard error of the sample statistic. We're going to talk about that in a second. That's this one, S sub p hat. This is the standard error. I'm just going to write SE. We see it right up there, SE, standard error of sample proportions. And notice here we're using p hat times 1 minus p hat over n. Okay, so slightly different. So let's fill that in on our stuff here. What is the mean of a sampling distribution? Well, the mean of a sampling distribution is equal to pi. You can also write it as mean of sampling distribution equals p. These are interchangeable. Again, Mr. Reboff prefers this one. The book uses this one. AP can use either one. It's perfectly fine. Standard deviation, the standard deviation of a population distribution is equal to square root of pi times 1, or sorry, times 1 minus pi over n, or circle that one. Again, I prefer that. That doesn't mean you get more points if you use it. It's just I think it's easier and makes for less mistakes. P times 1 minus P over n. Okay, either one of those is fine. This is what's on your formula sheet. So these are on the formula sheet. Okay, standard error, S of P hat. A lot of times you'll see it written as SE equals, okay, so that's pretty common, is equal to P hat times 1 minus P hat over N. Cool? And that's the same. Cool? So on our green sheet, make sure we have this filled in. That could be helpful, right? As we get used to these new symbols, right? Having kind of the vocabulary there for you is a nice thing, but it's all there. It's great. So what does this all mean? Well, let's go. Standard deviation versus standard error. They looked a lot the same, right? P, 1 minus P, P hat. This one uses the population parameter. This one uses our sample proportion, right? So one uses the parameter, one uses the statistic. Standard error does not mean it's a bad thing. We think of errors as a bad thing. Error is just basically another word for deviation. They used to call this sample standard deviation rather than standard error. Now they're using standard error, and I think it scares some students like, oh, error, you screwed up. No, you didn't. No, you didn't. That's just the general variability of a sample, right? Cool. All right. So standard deviation versus standard error. The difference is where the proportion comes from. Comes from. If it comes from the population, then we have standard deviation. If it comes from the sample, then we have standard error. It's just, it tells us, is this the population proportion or is this proportion coming from the sample, right? That's it. If you have both, use standard deviation, okay? So if you do have both, always opt for standard deviation. It should be more um, accurate. I know we hate that word, but right, it should be more better than the sample, right? Because of sampling variation, right? Sampling variability. Population should be spot on. Should be. Here we go. How to decrease standard deviation of a sampling distribution. So think about our standard deviation, right? Look at both of them, right? We know in math, right, if we square root a fraction, we can change that to square root of top and square root of bottom, right? So basically, we've got square root of this is equal to the square root of the top over the square root of the bottom, and the bottom is our n, right? So if I want to cut it in half, I'm going to have to divide by 2 more, but I'm square rooting it, right? So the square root of what would give me 2? Yeah, so to cut standard deviation in half, multiply n, our sample size, by 4. Right? So if it was 100, use 400, and that's going to cut our standard deviation in half. Multiply, sorry. To cut it by a third, this would need to be divided by 3, right? But we have to square root our sample size. So, yeah, multiply a sample size n by 9, because once we square root it, it's going to be 1/3 as much, right? So if this was 100 and we wanted standard deviation cut down, right? Less variability, that's a good thing. This would need to be 900, okay? Do you think that's a typical problem? Yes, it is. It's pretty common for multiple choice, right? To cut the standard deviation in half, which sample size would be needed? And they give you 5 of them, right? Look for the one that's 4 times as big as the original one. Make sense? Cool. All right, here we go. Pause for a second. There's people here. All right, so I told you before, like there's a reason why we have to understand sampling distributions because they're going to lead us to answering questions. And here's how it works, right? So we've got our sampling distributions. We're able to find, right, the mean and the standard deviation or the standard error, right? And if we know mean and standard deviation, we can use normal calculations. Okie dokie. So that's the idea that we're working with here. Okay, so we're going to lead up to that. To be able to use normal calculations, we need our um, we need a couple things to happen. One of the big things is we need our distribution to be fairly normal. Okay, is a big thing, right? So there's some rules to be able to use this normal calculation, and those things are called conditions. Okay, from this point on, everything we learn pretty much is going to involve checking some conditions before we use a certain thing. So we're going to learn tests, we're going to learn intervals, we're going to learn normal calculations right here. There's going to be conditions for use, and you have to check those conditions before you use it. Okay, so these are the conditions, the three conditions for using normal calculations with a sampling standard, um, sampling, can't even say this, sampling distribution of proportions. There we go. All right, so here's the conditions. Number one, condition one, we have some kind of randomness. Okay, sample is obtained randomly. That's usually stated. Okay, so look in the prompt of the problem. We're looking for words like an SRS was conducted or a random sample was taken, right? So we're looking for those words in the prompt stated in problem itself. So look for these words. If they say these words, then we met that condition. Okay. There's a large counts condition. Okay. So this is also known as the nearly normal. Nearly normal. This allows us that we have a big enough sample size that we're getting something that looks kind of normal, right? We know that as the sample size increases, we're getting more normal. This is our rule for when it becomes normal enough. Okay, so they are NP is greater than 10 and N times 1 minus P are greater than 10. So this is a sample size times the probability of success. So what this is actually the number of successes, right? This is the sample size times 1 minus the probability of success, which is the probability of failure, right? So this would be the number of failures that we have. Pause for a second. All right, we are back. Here we go. So continue with the conditions. We got randomness. We were talking about the large counts condition or the nearly normal condition, right? So we were saying this is the number of successes need to be greater than or equal to 10. This is going to be the number of failures, right? So a lot of times you'll see people do successes equal failures equal, and they both need to be greater than or equal to 10. Okay. So the whole idea again is as sample size increases, no matter what the proportion of success is, we get something that's more and more normal as we go, right? And this helps ensure that. Cool. The final one is the 10% condition. Okay. The 10% condition is that 10 times the sample size needs to be less than the population size. Okay. So what this does is it makes sure the population is large enough to support the sample, right? So if I gave you this like hypothetical, right? We want to know what percent of people are voting for a certain candidate, right? And I have a bucket, right? Or think about let's go with your favorite Skittle color, right? So I have a little cup filled with Skittles, and there's five Skittles in there, and one is orange, right? So if my population in there is five and only one is orange, and I take a sample of size, two or three, the proportion of successes changes, right? So I have a 1 in 5 chance of pulling out an orange one, right? And if I do, now I have a 0 in 4 chance of pulling out another orange one, right? The proportions change a lot with that small population size, right? If the population of Skittles in my jar was 200,000, and 10% of them or 20% of them were orange, right? And I pulled out an orange, the probability of pulling out the next orange doesn't change very much. Does that make sense? So my population needs to be big enough that if I pull a sample out, it doesn't change the proportions as I'm pulling it out. Does that make sense? I hope that makes sense, right? So we want a big enough pool to pull from. So as we're pulling from it, the probabilities do not change. Okay. And that's what the 10% condition does for us. Okie dokies. All right. So let's go in here and do a problem. Let's do it. So we're going to see how this is actually useful. We're going from kind of theoretical to actually how we use it. A Silicon Valley company with 2,100 workers has a workforce that is 35% Asian. There is some concern that of the 150 workers who were promoted last year, only 24% were Asian. So the company is 35% Asian. There was a bunch of promotions last year, and only 24% of those promoted were Asian. They're like, dude, this doesn't seem right. Okay, this seems wrong. So they're thinking about litigation. So lawyers considering a lawsuit against the company would like you to find the probability that a randomly selected sample of, and this has changed, this is now 150 workers would have 24% or fewer Asian workers. So they want to know, hey, if this was totally random, right? If this was totally random, what would be the chance that we would get 24% or lower, right? Is this a rare occurrence, is what we're looking for. Okay. So before we answer this, we need to check our conditions. Okay. Was the sample obtained randomly? Right. So we're going to read in here. So there's some concern 150 workers, blah, 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 would like to find the probability that a randomly selected sample of 150 workers. Okay. Stated. And you can even like draw a randomly selected. There we go. Large counts condition, NP and N1 minus P, right? P is the sample proportion. We have two proportions. We have P or pi equaling 0.35. We have our sample P, right? Our sample proportion is 0.24. So I'm going to use the population if they give it. So 0.35 times 150, right? So my sample size times the probability of success. So the number of successes would be here. And my probability of failure is 0.65 times 150 in the sample. Okay. Are those both greater than or equal to 10? Yes, they are both greater than or equal to 10, right? This is like, I don't know, 50 or something like that, right? And this is like, I don't know, 100 or something like that, right? We're pretty close. So we're perfectly fine there. I don't have to find these numbers if it's obviously clearly okay. All right. And then finally, the 10% condition, right? So is our population big enough to support this sample size? So 10 times our sample size of 150 needs to be less than our population, which is 2,100. Is this going to be true? 1,500 is indeed less than 2,100. So yes, we have met all three conditions. We can move forward and use this to answer some questions. Cool, we've met the conditions. All right, so let's find the normal approximation, right? So we need a mean and a standard deviation. My mean of my sampling proportions should be 0.35, right? The mean of the sample proportions should equal the mean of the population, which is 0.35. Okay, my standard deviation of the sampling distribution, I'm going to go to my formula sheet. I could have done that for the mean as well, right? So the mean of this is equal to the population, right? The standard deviation is population times 1 minus the, or sorry, population, the square root of the population proportion times 1 minus the population proportion over n. All right, so let's crank that out. So boom, boom, boom. We have the population proportion 0.35 times 1 minus 0.35, which is 0.65, all over our sample size, which is 150. I calculated that already, and that's 0.0, right around 39 or 0.04. You could round up to the 0.4 since it's so close. I like to keep it a little more, I don't know, a little more precise and go to that 0.39, 0.039. All right, so now we need to calculate the probability. Well, let's draw a picture of what's happening here. Okay, so we got our normal distribution. We should be normal enough thanks to our NP and NQ condition up here, right? So the mean is 0.35. We want to know the probability that's 24 or less. That's going to be somewhere over here, right? 0.24 or less. And my standard deviation of the sampling distribution is 0.039. I've got the mean of the distribution, right? And I want to know here or less. So what does that look like to you? Well, that looks like normal CDF to me. And I'm going to go left endpoint. I could use negative big number. I could use 0 in this case is perfectly fine. 0 to 0.24 with a mean of 0.35 and a standard deviation of 0.039. Okay, I'm going to pop that into my calculator and get a number. Oh, I thought I had already done it. Here we go. Let's go. Stat. Oh, sorry, not stat. Second distributions, normal CDF, never PDF, right? I'm going to go 0, comma, 0.24, comma, 0.35, comma, 0.039. And then I'm going to press enter and we have 0.0023. Okay, so the probability 0.24 or less is about equal to 0.0024, right? Or 0.24%. This is pretty rare, right? This is pretty unlikely if if this was true. So if this is true, right, to get this percentage randomly, and that would happen less than 1% of the time, I think they have a case for their lawsuit, right? This is unfair practices in their workplace. Sorry, you're getting sued, bro. All right, and that's it. We're on to additional practice. So if you want to pause now and do this and then check the answers after, that's perfectly fine. If you'd like to save this for later and then come back to it, that's fine as well. Okay, so pause or peace out or keep going. Here we go. Do you drink cereal milk? Right. So at the end of your, you eat your Wheaties or whatever you're eating, cornflakes. At the end, is there milk at the end? Do you drink it? Right. So that's the question here. This is actually from our textbook, problem 35 in chapter 7. A random sample of 1,012 U.S. adults were asked what they do with the milk at the bottom of their cereal bowl. Let P hat be the proportion of the people in the sample who drink the milk that is left when the cereal is gone. An industry spokesperson claims that their research has established that 70% of Americans drink their cereal. Okay, so that is the claim. That's going to be our pi equals zero point 0.7. Okie dokie. Okie dokie. All right. Let's see. All right, here we go. What are the mean and standard deviation of the sampling distribution? All right, the mean of the sampling distribution should equal the mean of the population, which is 0.7. The standard deviation of the population distribution, you'll eventually have this memorized, I think, is going to be P times 1 minus P over N. The more times you write it, the more it sticks in your brain. Not that you need to memorize it. Remember, it is on your handy dandy green sheet right there. So this is going to be 0.7 times 0.3, right? P, 1 minus P, all over our sample size, which is 1,012. Okie dokies. All right. I calculate that, and I already did that, so I've got it over here, 0.0144. All right. So the average is 70%, we would think. The mean is 70%, and we are plus or minus about 1.5% either way. So most of our samples should be within about 1.5% of 70%, right? Check the appropriate conditions. So randomness, let's check that one. It says a random sample. That's the very first words. So stated, and maybe I do that. There we go. Do we have nearly normal? That's our 10n less than p. Oh, sorry, not 10n less than p. My bad, my bad, my bad. That's the np and n1 minus p are greater than or equal to 10. That's what I meant. And is that true? I think it's going to be true, right? So zero point 0.7 times 10, 12, and 0.3 times 10, 12 are clearly both greater than or equal to 10. So we are good here. Ching. And then my 10% condition, this is sometimes called the independence condition. 10 times the sample size is less than the population size. Okay, so 10 times 10, 12. Is that less than the population? So that's 10,120 people, and our population of interest is US adults, is less than all US adults. So we are fine here, right? So we've met all three conditions, random, nearly normal, and the 10% or large counts condition. We met them all, so we can use this mean and standard deviation because we have a fairly normal distribution that's good in some other ways as well. All right, this poll finds that only 67% of the sample actually drink the milk. Is this result evidence against the industry spokesperson's claim? So here we go. Let's draw our picture. So we've got mean of the sampling distribution should be 0.7. I'm going to draw my standard deviation of the sampling distribution equals 0.0144. And we are looking here at 0.67, which was our sample proportion. And we want to know the probability of that. Is it normal CDF again? It is. Time for normal CDF. I'm going to put in 0.67. So that's my left endpoint, my right endpoint. My mean is 0.7. My standard deviation, I calculated to be 0.0144. That was up above right there. And what do we get? The probability that we are at 0.67 or less is going to be about equal to 0.019, right? So about 2%, right? So I'm going to answer this. Is this result evidence against the industry spokesman's claim? I'm going to say roughly 2 out of 100 samples of this size would result in a percentage 67 or less. This is some evidence, some decent evidence, I would say. Evidence against the industry claim. There we go. Right? It only happens about 2% of the time. That's pretty rare, right? And again, what is rare changes in situations, right? If I said, hey, you have a 2% chance of winning Mega Millions, right? The $2 billion lottery that's coming up. I don't know if it is or not. 2% chance of winning the big lottery prize, that's actually pretty likely, right? Compared to what you would expect for the lottery, which is like 1 out of 300 million or something like that. It's insane, right? So, 2% chance of your car's brakes not working, that's a really high percentage, right? We want a much lower percentage of that, right? So what is, acceptable or not, right, is kind of different. So this one, I'd say, hey, 2% of the time it would be this or less. That's some evidence. Maybe something's going on. Maybe it's actually lower. Again, we never commit in statistics, but that's low enough to say that maybe something's going on. Okay. What sample size would you need to do to cut part A in half? All right. So our sample size original was 10, 12. To cut it in half, we would need to 4 times the sample size, right? So 4 times 1, 12, 10, 12 would be not almost equal to, would be equal to 4,048. Okay. And if you got scared, you could check, plug it in here and see if that would cut it in half, right? Not a terrible idea. Let's try it. So square root, where's my square root? Square root of 0.7 times 0.3 divided by 4048 equals 0.00, oops, there it is, 0.0072. Is that half of 0.0144? Yeah, exactly. So we got it. Okay, we could check if we want to. And that's it. Pen drop. We out. Good job, people. See ya.